Hello, my name is Danilo Shafashek, my advisor's name is Milton Fujimoto, and I will present my work with the title Theoretical Study of Acrolein Molecules Photoionization. Acrolein is an organic toxic molecule produced by bacteria. It can be found in the chemistry industry, oil and gas industries, and additionally it is synthesized in incomplete combustion reactions inside engines. Acrolein intoxication can affect the respiratory and the nervous systems. Here we can see the molecular structure of the acrolein molecule, which has CS symmetry. We aimed to calculate the cross sections and the asymmetry parameter to photoionization of the valence orbital of acrolein molecules in gas phase with energy ranging from threshold to 40 electron volts. The photoionization happens when a photon is absorbed by the molecule and it causes the ionization of the molecule, resulting in a cation and a free electron. To describe the photoionization, we need to calculate the dipole transition elements. We can use two ways to calculate the dipole transition elements, the length form and the velocity form. They are equivalent in theory, just if the wave functions were exact. Here we can see the expressions to total cross-section and to differential cross-section. The total cross-section depends only on the scalar modulus of the transition elements. And the differential cross-section, that's related with the angular distribution of the electrons, depends on the total cross-section and on the asymmetry parameter. We can expand the dipole transition elements in partial waves to get this expression. And we can show that the asymmetry parameter can be calculated using only the dipole transition elements and the Clebsch-Gordan coefficients. So, all the photoionization is described by the transition elements. The wave functions were calculated in the Hartree-Fock level with August CPVTZ basis set. The orbital 2a'' of acrolein was studied. This orbital has a ionization potential of about 11.5 electron volts. Polarization and correlation effects are included using the Perdow and Zunger model potential. The cross-sections and the asymmetry parameter are obtained using the E+E computational suite. The E+E is based on the Schwinger variational principle and the Padé-Approximants technique, and takes advantage of single-centered expansion that expands all functions in a set of angular functions with adapted symmetry. Now we can see the results for the total cross-section to the acrolein valence orbital. The results are compared in the length form and the velocity form of the dipole operator. The cross-section has a peak at about 12.8 electron volts, and after that decreases to height energies. Here we can see the results for the asymmetry parameter. The two forms of the dipole operator do not significantly change the asymmetry parameter. Here we can see the polarization effect on the cross-section. Without polarization, the cross-section has a decrease instead of an increase just after the threshold. And now we can see the results for the total cross-section with the symmetry's contribution. The cross-section in the two forms of dipole operator differ because the approximations in the wave functions. However, the asymmetry parameter only differs slightly to height energies. The polarization changes cross-section behavior on lower energies. The greatest contribution in the cross-section comes from symmetry A', and the peak at about 12.8 electron volts shows that the photoionization is more likely to this photon energy. Here are some references, and thanks.